Hey, this is Horner. We're going to look at polarizers and changing polarization. So just looking at how we can take unpolarized light and make it polarized by using something called a polarizing filter. So typically it's just a plastic sheet, but it does have long organic molecules called polymers in there. And what that will do is that will allow only just one type of light to come through, just in one plane. So we call that polarized light. So as light enters the filter, the component of the electric field oscillating parallel to the polymers drives electrons up and down the molecules, and when it does that, it absorbs the energy from the light. So only the component of the light that is perpendicular to that really comes through. So you'll notice that these polymer lines are straight up and down, so the light that comes through is only going to be the one that's in the left, right, or the horizontal plane here. So the direction of the transmitted polarization is the axis of the polarizer itself, and that's what you would see. So when we have polarized light and it approaches a polarizer, the magnitude of the electric field of the light is transmitted is that incident light times the cosine of the angle. So transmitted is equal to the incident times the cosine of whatever that angle is. So the incident light is polarized at the angle with respect to the polarizer's axis. So here we've got this angle theta. And so the light coming out will be E cosine of theta. So only the component of E in the direction of the axis is transmitted is all we see. If I want to know the intensity of light, we can use Malices Law. And this one just says that the transmitted light should be equal to the incident light times the cosine of the angle squared. And that is Malice's law for transmission of polarized light by a polarizing filter. We can demonstrate this with two polarizing filters. So the first one's called the polarizer, that polarizes the light, and the second one is called the analyzer, and the analyzer is rotated by an angle of theta relative to the polarizer. So you'll see here is our unpolarized light as it comes through. I've got the polarized light now, and now I have an angle from where the analyzer is. That's the angle that we're referring to as we go through. So for example, let's say that the angle that I have is 0 degrees. That's going to allow all the light to come through. So you'll notice that the background is the polarizer, this is our analyzer, and we're letting all the light through. If we do it at a 45-degree angle, now we get a less intense light. And then if we do it at 90 degrees, we should get 0 light coming through. So two polarizing filters with perpendicular axes, we call those crossed polarizers. You can kind of think of this like a picket fence. So if I have a picket fence like this, and I have something trying to get through, it can only squeeze through these openings. And when it does that, then we can say that that light is polarized up and down. If I take another fence, let's take another fence and let's go the other way. So I've got another fence and I go this way. Where these two overlap, I would not have any light coming through at all right there. So that's what we're talking about when we talk about the polarizer and then the analyzer and switching those angles as we go through. So on the next one, you can actually use these really well. So an object placed between two cross polarizers can actually change the polarization of light so that the light is transmitted from the analyzer. So for example, different minerals and different material and teeth can change the polarization in several ways. So this is kind of the effect that you would see. And this can give an image of the different types of tissue that are in the teeth. So you can see all the different types of tissues based on their colors as they go through. In polarizing sunglasses, the polarization axis is vertical, so the light that gets through is only vertical light. Glare is the reflection of sunlight from lakes and other horizontal surfaces, so it has a very strong horizontal polarization. So vertically polarized glasses eliminate that glare. So just draw a really quick picture here. If I have a lake, kind of like this, and then the water is on the surface here, and I have the sun back here, the light from the sun is coming out in all the directions, okay, and it's going everywhere, but when it hits the surface, it only comes back horizontally. So when you look at that light coming off, it's horizontal. If I put on polarizing sunglasses, those sunglasses then have an axis that goes this way, and what that does is it blocks that glaring light from hitting you in the eyes. So a really good feature, especially if you're out boating. Here's a good quick check. A vertically polarized light wave of intensity 1000 milliwatts per square meter is coming towards me out of the screen. After passing through this polarizing filter, the wave's intensity, and for this one is going to be 500 milliwatts per square meter, because now I'm using that 1000 times the cosine squared of 45 degrees, and that will give me 0.5, and so it'd be half of that 1000, and that gives me my intensity of 500 milliwatts per square meter. And that is the end of the polarization talk.